Welcome back to Human Resource Machine. Alright, we're on 36. Alphabetizer. So we're now working with strings. Please advise this option. Yeah. The inbox contains exactly 2 words. Determine which word comes first if you were to order them alphabetically and send only that word to the outbox. What the heck? Okay. Fine. Sort of see what we can do. So we probably want to store the words on the board, separated by like zeros or something, so we can say, ooh, this one starts at 10, I see. So they're helping us here. Hello, Songo. Alright, so I guess I want to store the first word just from 0, so we do pick up a letter, we copy it to this address, bump this one, increase it, and jump back to the start. So that's the basic loop. Okay, now we need a break if we are holding the 0. Okay, I don't think we need this second counter actually, so we can do this. We can say if we're holding 0, let's say. We have to copy that first. So if we're holding 0, we jump out of this, move to the second loop. So the counter is pointing to the 0 we've just placed. We could actually reset. We can reset the counter to 0. Let's just try that now. Okay, fine. Now, we do this again. Take a letter. Let's copy this one and put it here. So we still have 10, because we'll need 10 later on. We'll need to remember where we started from. So we take... we copy to... No. Copy to that location. Bump. And repeat. Rinse and repeat. If with 0 we return. Okay, now we have to compare the two letters. Oh. Okay, I get what we have to do here. Okay, before we do any of this, let's just copy these counters to these, the bottom left corner. No. Copy from there. Copy to there. Copy from there. Copy to there. Alright, so we have resettable counters now. So here we're using that. Bump that. Okay. And here we reset that counter. Now we copy to okay, so now we are writing the new word, so that goes, uses that one, bump that one, and if we pick up a 0 again, we jump. Okay, let's watch this. Good, and place the 0. Good, okay, now what? We've done all that, that's fixed. Alright, next phase. So let's call this phase plate. Oh, I don't like this. I don't want to Okay, fine. Place words. Whatever. Okay, next phase is air. Okay. So in a loop, we pick up. We have to reset both these counters now. So we copy 10. So that resets that counter. Okay. Now we compare. So we pick up the first letter of the first word. So and we subtract the first letter of the second word. So it's 3 cases, if we're positive, negative, or 0. If we are 0, then we have to bump if they're equal, we have to go to the next letter. So we bump each of these to go to the next letter, and then we jump back to this. All right. If otherwise, we go down to this section here. So now we know which word to output. It will be, if we've got a negative, it will be the first word. So if it's negative, then we put the 0 here and put it here. Whatever ends up in 22, that's telling us which word we're going to output. Otherwise, we put the 10 there. That's just telling us take the second word. Okay, so we've decided which word. Finally, we pick up whatever this is, whichever word this is pointing to, and we output it. And we stop as soon as, well, it will stop automatically, won't it? All right, let's try this then. So we place the words unzip, unwed. Oh, I forgot to bump. Bump that. Untie. Undone. Yeah, bump codes after that. Whoops. This is basically lexicographical ordering algorithm. This is good. This is a good problem. This is exactly what... Wait, what are you supposed to do if they are... equal? You just output one of them. Okay. So... let's factor that in. So... this phase here is... output. So if... so if it's 0, we repeat. What if we pick up a 0? That means we're done. So we just do... we just output one of them arbitrarily. Let's say... the second one. Doesn't really matter. But that looks like it'll use one fewer command. God damn it. Oh yeah, of course. And if it's 0, we're done. That's an interesting problem. Not too difficult, but... oh. Oh. Damn it. Oh no. I didn't account for the fact that they might have different lengths. Oh, come on. Alright, so what would happen if we have different lengths? If we get a 0 in the first one, that means that one's shorter. So... shorter... wait, what? No, it's... if we get a 0 in the first one, that means they equal up to that point. But the first one is either shorter or the word is completely equal. In both cases, we want to output the first one. Alright? So, let's do that. So, compare. If we pick up a 0, we do that. What if we pick up a 0 in the second one? That means the right-hand one is more shorter, so... copy from... if the right-hand word is... if the second word is shorter, if we hit a 0, then we're going to get a positive number. So we're already outputting the second word, so that works out. What? You subtract 2 letters and you get a number, but you're not allowed to subtract... okay, damn it. Okay, fine. First, we check whether there's a 0 in 21. If there is, then we output the second word, which means we do this one. Okay. Well, that should account for that case. Oh no. There's still... Yeah. Okay. If... No. Haven't I... What's failing now? I thought that would work. Hang on. So, there was a 0. What was going on here? We're going for the second word. Why? So we got a 0. Okay, so copy from 21. Alright, so that's saying 12. Jump if 0. It's not. Alright, so now copy from 20. Jump if 0. We're jumping to the wrong place, are we? Can't even see where this arrow is going anymore. Then we should be going for the first word. Damn it. Okay. Nice. That's a cool program. Oh, very close. Don't care. Scavenger chain. Each pair on the floor contains data, the address of another of the pairs. A scramble chain. Each thing in the inbox is an address of one of the pairs. Output the data for that pair and also the data in all following pairs in the chain. The chain ends when you reach a negative address. Well, it's not too bad. Alright, so we pick up an address. We... Let's copy it to the center board, center square. Alright. Then we pick up whatever that address is pointing to. Output it. Then we have to bump that address to get to its corresponding address. We pick up whatever that's pointing to. Copy that to 12, and now we repeat. Right, so this won't stop yet, but let's just see it work. Okay, good. We've got an achievement for that, alright. So, we stop when repeat and... the chain ends when you reach a negative address. So when you get a -1, so when we pick up, what we do 12. So when we have a negative address here, we reset the whole thing. It's that one. What did that say? Escape? Nice. Digit exploder. Grab each number from the inbox and send its digits to the outbox. For example, 123 becomes 123. Okay. So... interesting. So we want to figure out how many hundreds there are. So we pick up the number. Put it here. Now we subtract 100. If that's negative, we do this. We what if it's not negative? We will hang on, setup. We need to first put zeros. One, two, three. Okay. I need to put that here. Here. And here. Those are the zeros. We need to bump that so it's a 1. Then it's all set up correctly. Alright, so if we subtract the number and it's not negative, then we put our number back where it was. And we increment the counter. That's because we found another 100. So we keep subtracting 100 until we can no longer subtract 100. And if we are negative, we break out of that loop. Alright. Let's check that works. Okay, so now we've got the hundreds. Now we just have to repeat this process. So we have to say... So we've now got a number which is strictly less than 100. You know what? We don't need the 1. We can take that one out. We don't need the 6 either. No, we don't even need the 7 actually. Oh, we do. Okay, so at this point we pick up our number, which is stored there. We now want to count how many 10s there are. So we sub 10. We copy that number back to 2. We bump the number of 10s. And then we pick up our number, jump back to start. We can take that one out. So if it's negative, then we're done with that. So then the final step we do is we're now holding on to a number that's strictly, if it's negative, then we just pick up our number again. Because now it's, wait, no. If it's negative, then whatever we had before, so add the 10 back. Put that. No. Which order are we? Oh, the hundreds first. Ah, but we probably don't want the... Okay, fine. So add 10, put it in 6. So if we've done this, we'll now have the hundreds in 8, the 10s in 7, and the 6, the 1s in 6 units. Now, we pick up the hundreds. I guess we don't want to output leading zeros. So we will have to skip ahead. So if it's 0, then we skip the outputting. Alright. Then we copy from here. We have to jump if 0. And then I guess the units we have to output, so... And jump back right to the start. That's cool. What was the input which fails? The number 1? Yes, here I'll give you some inputs that cause your solution to fail. Where? Where? Oh, it fails on these next ones. Oh man. What do we do about the 0 in the middle? So if there's a 0 in the 100 space, we absolutely skip that. If there's a 0 in the middle, now that's a problem. We have to check the hundreds. Okay. So if we've got a 0, we now have to pick the hundreds up again. Wait, no. Yeah, we pick the number of hundreds. And if it's 0, that's 0 too. Then we skip. Hello, Shawnee. Have you played this? I played the sequel before. What was it? 7 Billion Humans. But I never knew there was a prequel for a long time. Alright, well, now I lost my train of thought. Where was I? So if we pick up the hundreds, so if the leading digit of the number of hundreds is 0, that's fine, we skip it. If the middle digit is a 0, we then have to go back and check the hundreds, because if the hundreds was also 0, then we skip it. If it wasn't, then we don't. Hang on, so I've handled the hundreds. Faye has, okay. It's a good game. It's a good game for introducing to the concept of programming for those who haven't, but also fun for those who have. It's actually pretty frustrating for those who have, because you want to be able to do while loops, and you want to be able to comment your code nicely and stuff. It's hard to think about this stuff. Alright, so if the middle digit is a 0, right, if it's not a 0, we just output it. And move on. If it is a 0, we have to go check the hundreds again. And if that was a 0, we skip everything and go to the units. If that wasn't a 0, we have to go back and pick up the 10s. Which we know is a 0, and output it. And up here, if it was never a 0 to begin with, then we have to skip to this bit here. Let's try this. So yeah, this problem is basically to take a number and turn it into its hundreds, tens, and units. The tricky bit is the 0 in the middle. Okay, 30 commands. I'm not too bothered with these extra challenges usually, but I mean, surely I can eliminate 2 commands. It's this nonsense here in the middle. I'm sure there's a cleaner way of dealing with the 0 in the middle. Do they care about leading zeros? Nah, they probably do, so... Nah, not bothered. Move on. Re-coordinator. Oh no. Okay. We're gonna split these numbers into the 2 digits, aren't we, or something? Each number in the inbox is an address of a tile on the floor. Send to the outbox the coordinates of that tile, column first, row second. Oh. Wait, so this is what... So... Okay, so if we pick up a 4, we're gonna go to this tile here. Ah, so we're doing modular arithmetic, basically. We're saying the first column is going to be that number modulo 4, and the row is going to be that number divided by 4. That's why they've got a little 4 down here. Okay. So we've done both of these operations before, haven't we? So okay, pick up the number. And we do, what's it called? The Euclidean algorithm of division. One of the first documented algorithms, I think, in history. So but we do the slow way, so we just repeatedly subtract 4 until we are less than 4. And then we're left with the... whatever, so we keep subtracting 4 until we're less than 4. That gets rid of all the 4s, and we're left with some number less than 4, and that is going to be the column. So then we output that and then go back and pick up that count that we had. So let's see, we need a count. So we need to pick up the count. Let's stick it somewhere. Let's put it here. So we're going to say, we're going to take our number. We're going to... Okay, I realize how I could have eliminated instructions from the last problem, but I'm not going to worry about that now. So we're going to subtract 4. as soon as we become negative, we break out of this loop. So we subtract 4. Then just go back to here. So we just keep subtracting 4 until we're negative. Now we add 4 just once, so we get back into the positive, but we're always going to have a number between 0 and 3. Let's test that. So if we do 5, we should end up with 1. But we'll dip below 0, and then we'll go back up. Okay, good. So we put that one... We output that one. Oh! I need to keep a running count here, so... We have to store that number somewhere, so... Okay, so we copy that here, we store that number here, we bump the counter, because that's counting how many 4s we're subtracting. So at this point, okay, let's assume that's all right. So now we output this number. So this is just going to be the number modulo 4, so 0, 1, 2, or 3. And then we pick up the counter, and that's going to be the number of 4s that cleanly divided into it. And output that. And then we just do the whole thing again. Let's watch this. Oh, stop. I didn't pick up what was in 3 after bumping. So we need to pick up, after the bump, we have to pick that back up. So that the invariant is, yeah, okay. Stuff. It's a very inefficient way to calculate modulo and division, but actually it's not that inefficient. An efficient way is just to use your computer's arithmetic and logic unit to do things really fast. Prime factory. So this is the last optional challenge, so it's probably going to be hard. Oh, it's going to be primes or something. Output all the primes. For each thing in the inbox, send its prime factors. This is technically hard. And when I say technically hard, I mean this is the sort of stuff that bank encryption uses. Like, if you could compute prime factors quickly, then you'd be able to break bank encryption, so it is by definition hard. Send us prime factors. That's what Big Bank wants you to believe. Really, everyone's password is just Superman. Actually, I think nowadays it is actually quite... We are actually at the stage where it's pretty easy to prime factorized numbers, but most encryption uses more advanced stuff, I think. Elliptical curve generation and some stuff like that. Alright, so let's think. If we had a number, you would want to see... Okay, 1 is not a prime factor. You're not allowed to use 1. So you start from 2. If 2 divides into your number... Oh man. But... Okay, we use trial division algorithm, which is, of course, another inefficient way of detecting prime factors, but this is what you would do if you didn't have... Alright, so for each number, 2, 3, 4, 5, 6, 7, 8, so on, we see if it divides into the number. If it does, we divide out that number fully until there are no more of that number in there. So our numbers, so if we started with, say, this is not a good example. Okay, let's say we've started with 15. We see if there's any 2s in there. There aren't any. Okay. See if there's any 3s in there. There are. So we divide by 3 over and over again until there's no more 3s. So we end up with 5. Now we see if there's any 4s there. Now we see if any 5s are there. There are. We do it again until we end up, until our number is just 1. That will get you all the prime factors. How do we do that with drag and drops? Okay, so we would need to start from 2. Let's make a 2 then. That's something. Let's test our code. Yeah, we got a 2. Okay. Now what? We take our number, which is going to be from the inbox. We store it in that square there. So that square is going to hold our number, and whenever we divide out numbers, we manipulate that number until it's run out of prime factors. Okay. So now we've got a loop here. We want to say we want to pick up yeah, let me think. All right, so the clean way of doing this is we say we pick up. Oh, okay, we're holding on to our number right now. So we subtract, let's say 2. 2 is the number we're trying to divide by. So we just keep subtracting 2 over and over again until it's either 0 or negative, which will eventually happen no matter what. And now those 2 cases describe 2 different situations. If it's negative, that means 2 didn't divide. If it's 0, it did divide. So the easier case is if it was negative, then we just move on to the next number. So we bump the factor And we jump back to the beginning of this this algorithm. So we're gonna have to pick up whatever's in 4. All right, and then we just repeat that with the 3, and then the 4, and the 5, and so on. Okay, so far so good. No, that's not a jump. That's a... It's negative. We jump there. Wait. Let's say we start from 1. So the first bump we'll put it at 2. Okay, that works. Alright. If it's negative, we'll then move on to the 3. Pick up our number, try and subtract repeatedly. Wait, why is that bump there? Oh, okay, take that out. Now, the other case is if it's equal to 0, that means we've got a prime factor. We need to count how many subtractions we did. So... let's say... we put a 0... What number, what space shall I use? 12. 12 is going to be... I should probably start using labels. 20 is the factor. Four is our number, most generic way to describe it. 12 is... what's the term? The result of dividing the number by the factor. I don't know, just call it result. No, the division. Let's call it division. Div is... okay. Let's just call this 0. Then it's clear what its purpose is. Its only purpose is to be 0. So we take the 0, we reset the division. I'm on like the second last level, and this is the first time I've been using labels properly. Right. And then we do all the factor stuff. That's fine. This level needs labels. Yeah, it helps a lot. All right, so we now begin subtracting our factor. Let's call this one just, I can't even, just call it temp. Because this doesn't really have a purpose, it's just somewhere we're putting down our number so that we can increase the division count and then pick up our number again. So we we just put what we're holding here, increase the division count, and then pick up temp again. All right. So we're still holding the result of subtracting the factor. And the moment it's negative, that means division is useless, and we'll move on to the next factor. So we reset division to 0, bump the factor, move, carry on. Okay, good. If it's 0, division should correctly be telling us how many times we did the subtraction, right? Sub. Yeah, because every sub is paired with a bump. Okay. So we output the factor. That is the prime factor. And now we replace number with the division, because we've now divided out that factor fully. I feel like someone who hasn't done, you know, at least a bit of number theory and mathematics would actually really struggle with this. But it is an optional problem, so. Copy from division. Copy to number, because our number is now replaced with that. And now we jump to the next factor. So we just jump back here again. Either way, we jump up there. All right, but this goes on forever. When do we stop? We stop when number is 1. So here, after this, after we pick up number, we look at it. If it's 1, how do you compare with 1? All right, we need a 1. But what's the cleanest way of checking if it's 1? All right, just we're gonna have to make a 1. To begin with. So we pick up our number. Ugh. Okay, well, we're gonna have to subtract 1. If it's 0, we don't have to output any more factors. We actually go all the way back to here. Otherwise, we just have to pick up our number again and just carry on. Wait, why is... Okay, outbox doesn't look like it's ever going to be hit. Copy from factor, outbox should be there. Yeah, okay. Let's try this then. Slowly. So it's setting up. Oh, I forgot to bump the 1. There we go. Okay, we put 1 as the factor. 11 is the number. But we start with factor 2, not 1. So we start with 2. We... Those... What the... Why did I subtract 1? Instead of factor. Sub 1. Oh, no, that's correct. That's correct. That's just what I did. Check if it's equal to 1. Okay, start again. Okay. Alright, so... we check. If it's 1, it's not. Okay, right. So we try to subtract 2 over and over again. We've subtracted 1 2. Subtracted 2 2s. Subtracted 3 2s. Right, that's correct, because we're not going to be using that number anyway, so it's now resetting everything. Increase that. Now we check the next number. Check if it's 1. We're checking for 3s now. Okay, now this is just going to go on and on, because 11 is prime, so... it's at 4. So if when we get to 11, it should be a factor of itself. Of course, the more efficient way to do this is to not go from 2 up to 11. Instead, you go 2 up to the square root of 11. Because it's easy to see you never need to go beyond that, but I can't think how I would tell it to stop there. Probably is a way. I mean, that's a massive improvement, going from a number to the square root of that number, in terms of how many operations you do. In the case of 11, you would only check 2, 3, and 4. No. 2 and 3. The square root is between 3 and 4. So you only check 2 and 3. And then you know there can't be any factors greater than 3. What are we on? Oh no, oh no. Oh no, 29, yeah, that's fine. Oh, something's wrong here. There shouldn't be a 3 in number. That 3 should have gone... it should have been divided out. Damn it. What happened? Oh, we've changed the numbers now. Hang on, what happens? So I wasn't paying attention, but we had our number was 29. Was it? Okay, I don't know, try a different set of numbers. And then next time I'll debug it properly. So, we divided by 2. Okay. Now we're checking for the 4s. Ah! Oh no! What am I doing? You don't divide. You don't change number to be the division of the number. No, hang on. That's wrong. No, you're repeatedly dividing by 2 until there are no more 2s. What I'm doing right now is just one division of 2. Hang on, I've got myself confused now. Okay, so it's actually more complex than this. But it's probably not far off. Okay, so we've got... No. Undo. What did I just do? Okay. So we divide by 2. Okay, so if it's a 0, then what are we actually trying to do? We know that 2 is a factor. So we output 2 as a factor. But we now have to keep dividing that number into... keep dividing number by that factor until there are no more 2's in it whatsoever. That's not what I'm doing. I'm just doing one division of 2. So 20 divided by 2 will be 10. But no, we want to end up with 5. So we want to do 20 divided by 2. And then divide by 2, and then divide by 2 over and over again until we reach a point where it doesn't divide. How do we do that? We... So we keep dividing by 2 until... So we don't change the factor. So if we found a factor... we output it. Alright, so from here, we have to have a new loop in here, which is where we keep dividing number by 2 until there are no more 2's. We can't do it up here because it's sort of interfering with that stuff. So when we get to this point, that's the first time we found that factor in there. Is it? This jump is taking us here. Yes, okay. So that's, we only do that once, we don't do it again. So after this point, we copy, so let's say 20 divided by 2 is 10. So division will say 10. We copy 10 to number, correct. And now we do this loop here. So we have to say we pick up number. Okay, we're holding on to number here. We now just do what we did above. Okay, that's not actually that complicated. Okay, so we now reset division. So we copy from 0, copy to division, So this is a loop here, so just make sure we remember that. So or this whole thing was being repeated. Alright, so now we try to so we pick up the number again, subtract the factor as before, we copy it to temp, we bump the division, pick up the temp again, now we know we'll never get 0 here because oh, no, what am I saying? We could absolutely get 0. No. Yeah, we can. That would mean we would just go for a next... Okay, fine. So let's see, what are the possibilities? If we are negative, that means we finally found the point at which we can no longer divide that number. Okay, if we're negative, hang on, so this has to be repeated endlessly. So if we're negative here, then all right, there's a why do we have these two jumps here? What's going on here? That's wrong. Oh, no, that's fine. Okay. If we're negative, what? That means there's nothing left to do. We actually move on to the next factor. So we go all the way to... here. But if it's 0, then we're going to have to I'm not sure why I have this jump, take that out. If it's 0, then we do this. That means it is evenly divisible by that number, so we have to put the division in the number, reset the division, pick up the number again, rinse and repeat. So we just keep on dividing to whatever the factor is over and over again until either it's negative, in which case we never have to divide that factor again. We can now go back to this whole process, or it's 0, in which case we go to the next process of dividing by that number. There's something may well be very wrong here, but let's try it then. So 8 is a good example. So now we take the 4 and we try and divide out the 2's, and now we take the 2 and try to divide out the 2's. We get to the 1. Alright, well it works for these cases. Let's see if he's happy with it though. I mean, if it works for the 8, which is 2 times 2 times 2, then that looks good, because that was the big problem. It was just dividing by 2 once, and then setting our number to be 4. But instead, we want to divide by 2 and again and again and again until there's no more 2's, in which case we would end up with 1, not 4. Management expected 2, but you outboxed 13. What? For what number? What were the original numbers? 13... 0 was a step at the end. Then he just slapped it on the belt. Sorry, don't follow. Let me see him do it. What was the original number? It was 13, wasn't it? So... what's the problem? 13 is a prime factor of 13. Why? Oh, are we still on the previous number? I don't think I... What was the previous number? I think he was expecting more factors for the previous number. Do I go all the way back? If I press stop, he's going to give us different inputs. I don't know how to go back all the way. I'll just keep clicking this. I don't know, let's try a different set of numbers then. 16, 10, and 12. So, for 16, the prime factor should just be 2. 10, it should be 2 and 5. And 12, it should be 2 and 3. So we should see 2, 2, 5, 2, 3. Alright, so we're going to be dividing 2. We should end up with 8. Okay. Now we do this bit. Now we should end up with 4. Then we should end up with 2. And then we should end up with 1. Okay, so now we're on to the next number, which was 10. So we divide out the 2 and we get a 5. Okay. We just wait until we get to factor 5. Alright, now we've got factor 5. Management expected 2, but you outboxed 5. Oh! They don't want the unique prime factors. So if... That's ambiguous, but okay. So 4, the prime factors are 2 and 2. But I would normally say the prime factors are 2. I wouldn't say 2 and 2, because those are the same prime factor. But he wants us to list it each time it's found. Okay, fine. I can do that easily. So what's the correct way of saying that? I guess full factorization is what he wants. Okay, fine. So the moment I had... Oh, that actually simplifies this then. Because we can just reuse old code, so we can actually say... We simply don't okay, fine. We just get rid of all this. We simply... Okay, get rid of all of this stuff after the outbox. Alright, so at this point, we did the original factor division, and we outputted the factor. The only question now is, do we increase the factor by 1 or not? We only increase the factor by 1 if we had a negative. If we had a 0, all right. All right, here's a hack. Instead of trying to organize that code, let's just say we decrease the factor now, because we know we're going to increase it, and those will cancel out and it will stay the same. So what I'm saying is, every time we do our division, if it cleanly divided, then we don't increase the factor. We just cleanly do that clean division, replace number, and now just go back up and try and divide by that factor again, which is what we're already doing. If it didn't cleanly divide, then only then do we move on to the next factor. Let's try that. That's actually good that they want that, because it's actually easier. Wait, what happened here? I didn't replace... Hang on. Or what was it? It was 14. Hang on. So after the 2, I outputted the factor. I didn't replace number correctly. Why not? Because number got replaced. I must have deleted something I shouldn't have. Okay. Copy from division, copy to number. That always gets done. If it's negative, we don't do that. If it's 0, it divides, then we do. Okay, try that. Well, these are prime factors, so this is not a good example. Let's reset. Try and find one which isn't prime. Okay, this one. So we should get 2 and 3. Now we're trying 2 again. And now we go to 3. Yeah. Oh, now we have to wait for 11 to be resolved, and then 12 it should be 3 and... It should be 2, 2, 3. So I think the way to be not completely unambiguous is to say share all non-unique prime factors, and if you wanted to share the unique ones, then you'd say unique prime factors. So unique prime factors would be 2 and 3. Non-unique prime factors would be 2, 2, 3. Wow, I actually got the size challenge. Speed challenge. I bet you have to do what I was saying before. You have to stop at about square root of that number, because that stops you doing lots of steps. That will square root the time it takes. Literally square root it. No, not quite. It would square root the time it takes for each individual number. How would you do that? You would... I guess you can just make an assumption that there is a cap on the size that they'll give you. It seems they don't give you anything more than like 30 or something. Square root of 36 is 6. So you can say the prime factor will never be... I don't know. There's some clever thing you can do. I'm not going to worry about that. I wonder what the lowest commands are for it. Yeah, I'm not sure. Something... I'm not sure you could really get away with. Going much lower than this. Because this is trial division. This is a tried and tested, efficient way of finding prime factors. Yeah, can't really think of any clever way of skipping stuff. Alright, sorting for. Is this the final proper level? For each zero-terminated string in the inbox, sort the contents of the string, smallest first, biggest last, and put the results in the outbox. Oh, so you can get numbers and letters. What is this code they've given us? Let's put a 0 there, he's put that there. Oh, okay. He's putting the number down for us. That's nice. So we want to... So we've got the string, and now we want to sort it. I mean, we did this before, but it was just sorting 3 numbers. Now we want to sort a number of indeterminate length. Okay. Well, I think we just do what we did before, essentially. Bubble sort. It's the easiest to program using basic commands. But is he putting the 0 down? He is, yeah. Good. We need the 0 then. Okay, so bubble sort says you look at the first 2 numbers, you swap them if you need to. So the smallest goes to the left and so on. And you look at the next 2 numbers, swap them if you need to, and do that all the way to the end of the string. And then do that whole thing again n times. And then you're guaranteed all the numbers fall into the correct place. So we need an outer count and an inner count. So let's think. When we do this, what will this number be saying? 3. Exactly what we need. Okay. Okay, so let's call this inner and outer. Let's call that 0. So we copy the inner. Inner is now the number of characters in the string. Copy that to outer. Outer is going to tell us how many full pass sweeps we need to do of the whole string. Inner will point us to each element of the string in turn. Okay. So we basically want to reset inner to be 0. Alright. Now we begin. So we say let's pick up the second. All right, so let's actually bump inner. So we start from 1 because we're comparing pairs. So let's start from the second item, compare it with the first. Oh, this is a bit. Okay, fine. So we pick up the... Damn it, hang on. All right, you know what? We're going to need 2 variables. We're going to need inner and we're going to need inner plus 1. So let's say this one is inner plus 1. And that one is outer. Okay, so from inner, we copy to inner plus 1, we copy to outer. Alright, and then we bump inner plus 1, so that it's always 1 more than inner. This will help us. Then we copy from 0. Wait, what? Ah, wait, no. Take that out. Copy from inner, copy to outer. Now reset inner to be 0 and increase inner plus 1. Got it. Okay. Now we pick up. So now we've got a loop here that we do. So we pick up the second of the two items. So that'll be referred to as inner plus 1. And we subtract the first item. So that will be inner. That's why we have inner and inner plus 1. Now we'll end up with a number regardless of whether we had letters or numbers. If it's negative, that means a swap is needed. So no, if it's 0, hang on. Copy from inner plus 1. Okay. If inner plus 1 is 0, then we've actually finished one pass of the inner loop. So we bump outer. No. We subtract 1 from outer. And then we go back to this whole loop. To where? Here. So now we reset inner to be 0 and do all that again. But if outer is 0, that means we've done the inner and the outer loops. We've done the quadratic number of steps, basically. So now we're actually done, and we move on to the next phase, outputting. Okay. And the one thing I've missed out is, what do we do when we have a negative here? So we subtract inner. Subtract the first from the second. If we get a negative, then yeah. Okay, so if we get a negative, that means we have to swap the two. How do we do that? So we pick up the first... No. So we pick up the first item, place it temporarily here, pick up the second item, place it where the first item was, pick up the thing we stored temporarily, and put that where the second item was. Okay, so that swaps the two. And if it wasn't negative, then we don't do any of that. Okay. Either way, whether we did the swap or not, we now have to bump inner, bump inner +1 to move on to the next. And then we jump here and do all of that again. Let's see what happens. Okay, so copy from 0, copy to inner. Oh yeah. Copy to inner +1, bump inner +1. Yeah, okay. Okay, it's now in sorted order. So then the next phase is so now we just reset inner. We pick up whatever inner is pointing to, output it. It's smallest first, right? Yeah. And then we just repeat. And then we bump inner. We repeat. And as soon as we're holding a 0, then we are done and we move all the way back to the beginning and move on to the next number. Let's try that now. So if you do this n times, then you guarantee, even in the worst case, you get them all in sorted order. You do n full passes of the string. One pass means going from left to right, swapping. What the? Copy from inner +1. Inner +1 at this point is after the 0. Why is that? What happened to the 0? We've overwritten the 0. Damn it. Where's it gone? Our temporary variable here is where the string could be. Hang on, that's bad. Very bad. Yeah, so 5. That was a bad choice of number. Let's go for 23. That's just a temp variable. Alright, this looks like it'll work. Swap the 44 and the 96. More cardio for better code. This is the big one. So this is 10. Oh my god, this is gonna take 100 steps. Alright, well. Sit back and enjoy Bubble Sort. Even Barack Obama knew that you never use Bubble Sort. Unless you're playing this game, of course. I mean, could I feasibly do one of the better sorting algorithms? Not really, because you need... You need the concept of arrays or linked lists, which you can't really construct with the tools we have. Like, insertion sort is a good sort where you... I mean, okay, bookshelf sorting. When you sort books on a bookshelf, normally you would take a book, you would find the correct place to put it, and you would just push all the books to the side in order to put your book in there. That's insertion sort. You can't really do that here because you have to push a whole stack to the right by one, or by left. Which you can actually do, but that in itself just seems like it'll... It might technically, even if it's messy to code that, it might actually run faster than what I'm doing. Because that's sort of more efficient, but is it? Bubble sort is n squared time, insertion sort is n squared time. No, they have the same complexity. They're both quadratic. No, if you want to use a good sort, you have to do merge sort, which is, I don't know how you do that in this. Quick sort. If we had random numbers, we could do quick sort. That's actually a really nice way of doing it. I am curious how people halve the time, though. Maybe insertion sort is actually, in practice, ends up being faster than this, even though they're both quadratic. GG, question mark? Let's see.
Congratulations. You've really become an invaluable instruction follower.
Yes, don't worry. Your job is safe.
I hate the word invaluable.
Electric box.
It's called...
Just call me valuable.
Computer. It iterates through a list of simple instructions called a program.
Oh no. This is gonna destroy business. This is gonna... Well, not destroy business. It's gonna destroy the employment.
Instructions can be used together in infinite combinations to compute just about anything you can imagine.
A truly efficient worker that never sleeps.
It's going to change everything.
Please take your things and enjoy whatever it is you people do out there. Congratulations.
Guess I'm out of a job then. They have a computer now. Okay, so all this was going on outside. We weren't really paying attention during the game. We were just sorting boxes and stuff. And there's a whole war happening. Earth is being invaded. Pretty cool. That's actually better than what I had read in the reviews. I saw some reviews complaining that they found it, compared with the second game, they said this one was a bit too assembly code-like. It was a bit more assembly code-like, but I didn't find it frustrating at any point. I'd say it's pretty comparable to the second game. The second game is better, but this one is a worthy, I mean, first game in the series before moving on to the second one. I didn't find those codes actually, even in the optional ones, I didn't find them overwhelmingly complex. Maybe if I go for the challenges, it might become a bit fiddly, but they do actually give you a copy-paste feature where you can, well, not in-game, but you can copy your code in-game. You can paste it to Notepad outside of the game, and then you can do your editing and pasting or whatever, and then you can paste it back in. And they let you do that, and it works. If you press Ctrl-C, press Ctrl-V, it knows how to copy the format. So you can use that to help you if you need to, say, copy a loop 10 times or something. Because the silly thing is, if you want to do something 10 times, normally you would put a jump. The problem is reading that jump, that one instruction called jump, incurs a time penalty. So it's actually more efficient to just paste your block of code 10 times in a row if you're going for number of steps executed efficiency. Which of course is really annoying, but that does get you a faster speed, runtime. So you sort of have to eliminate the jumps if you want to go for runtime execution. Speedrun when? I wonder what they do about the speedrun, because I guess you're not allowed to paste in what you've already pre-prepared, otherwise you're literally... There are several games that have this feature where you can copy and paste blueprints in. Factorio is one big one, and they don't allow pasting in of blueprints except in New Game Plus. So they've decided New Game Plus means... I mean, beating the game Factorio doesn't actually unlock anything, but they've decided that a New Game Plus means you're allowed to use any blueprints you've previously devised, which means you can copy and paste any blueprints in. So I guess a similar rule set would be used for the speedrun here. It's like, well, they probably don't have New Game Plus because that's kind of dumb in this game. You'd literally just have the code for every... There is paste and no paste categories. So paste category must be really dumb then, because you literally have the answer for each level in front of you. It's just a question of how quickly you can alt-tab and how quickly you can paste them. But okay, fair enough. It's technically playing the game within the rules the devs intended for. So yeah, that makes sense that would be the any percent. Haste any percent is 7 minutes 50. That's longer than I thought it would be, but I guess you just have to watch all the... I guess they come up with code that minimizes the runtime of the average runtime of whatever sample they give you. And the thing is, for the prime factors one, well, that's not needed for, well, maybe for 100% is. Well, for some of them, you might not like the input they give you, so you could re-roll the input until you get smaller numbers and then run it, and then it might run faster. There's no 100% no pace. Yeah, it makes sense, I guess. If that prime factors one was a mandatory level, then I would definitely reset until I got some smaller numbers, like 10 or 11 or something. So that is a factor too. It seems it's not something I would like to speedrun because I'm not fast with a keyboard and mouse, but that seems to be the key. But, another one is Colobot. Colobot is an open source game where you can write code in the game and you can program Mars rovers to go around and do mining and stuff. I think the any percent is quite funny because you can actually write code which is meta code and actually breaks the level and kind of changes the level variable to bring you to a later level. And there's another game with coding in it called Else Heart.break, which is a very strange game because it has a story and you're a guy walking around in some town, but then eventually you find you're able to code and rewrite the mechanics of the things in your world. It's an interesting game. I might stream it at some point because I never finished it. But I guess there's some weird stuff you can do for the speedruns for that. So yeah, speedrunning programming games is a very strange thing. I guess it's a thing. So yeah, okay, that's Human Resource Machine. Will I go back and do the challenges? I said I was going to, but now I'm not sure whether they're actually fun enough for me to actually want to do them. I'm not sure. I'll think about it. But probably no. I think I'd rather just play other puzzle games than do all the challenges. Alright, it's 1 AM. I'm supposed to fly to UK tomorrow. Actually, no, Abu Dhabi, and then fly to UK the next day. So I really should not have been playing this, but I just really wanted to finish it because I might not be able to stream it for several days now. The irony is that I'm leaving Asia to go to UK. It's actually going to be hotter because there's no AC in UK. Even though it is technically hotter here in Asia, but I'm going to be sweltering in UK. It's not good. I mean, the main reason I'm going to UK is because all my bank cards have either expired or been cancelled due to stupid reasons. So I need to physically go there to get my bank cards because the banks are idiots and I can't get them to... I've tried to get them to send the card here and it doesn't arrive. Maybe it might arrive after months, but I can't wait months because I have no money. So it's like... I'm in this stupid situation where I literally have to fly to the UK just to pick up a bank card. It's dumb, but... While I'm there, I think I'll buy a new gaming laptop. That will make it worth it. And then I can continue streaming retro games. So it'll be pointless, but whatever. I like having a high-powered graphics card to play dumb stuff like Acid Dreams. Alright, thanks for watching, Shawnee. Probably in a few days I might stream some game if I settle in some hotel or Airbnb or something in the UK. And it's not too hot and my laptop can actually survive the heat, I'll be alright. Alright, see you.